Welcome to this special episode of Into the Impossible with yours truly, Dr. Brian Keating. Today we're joined for a special lecture by Dr. Brandon Hensley of Princeton University. He is a Lyman Spitzer Fellow, which is quite an honorific. Lyman Spitzer is the father, in some ways, of the Hubble Space Telescope, and Brandon is an expert on all things cosmological, but in particular on the peccadillos of cosmic dust, that most mercurial substance that forms the composition of our cosmos, that leads to the creation of cosmic worlds like our Earth and the destruction of Nobel Prizes, as you may have learned about in books such as Losing the Nobel Prize, over here, over there. And it actually makes up a good deal of the concern of the pursuit that we have as cosmologists, trying to seek out the birth pangs of the Big Bang and the inflationary B-mode polarization. It's an obstacle, but it also provides us a window on our galaxy to learn about it. It may also hamper our ability to measure the early universe's other features, such as its ability, our ability to measure primordial parity violation, which is of great interest to physicists. I always say that if we were to measure the violation of Lorentz invariant symmetry, that might be even more spectacular than measuring the departures that would be present and revealed by primordial B-mode polarization patterns. Many people suspect that the universe underwent a brief period of inflation or something like it, but almost no physicist believes that special or general relativity exhibits some form of parity violation or some form of Lorentz violation. And those types of claims have been made recently. Cosmic parity violation by Miami and Komatsu. I've had Sean Carroll on the show. I'll put a link to that up here in the card, and I'll put a link at the end as well. And that caused quite a stir when that paper was released back in late 2020. You'll see that Brandon is a little bit skeptical about that, along with his colleague Susan Clark, who's moving to Stanford to start an assistant professorship there. They're both the co-leaders of this paper that Brandon's going to be discussing, and they're both members of the Simons Observatory. I can't be more excited to have these geniuses as members of the team that I get to participate in, that we are in the midst of building, despite the many setbacks that we have along the way with COVID and other logistical challenges. We're hot and heavy on the trail to detect the most mercurial of all cosmic signals, its polarization. So sit back and enjoy this special lecture. Very technical, but I know you guys are up to the challenge. And stay tuned for more great talks. We're going to have a special lecture by our special conversation with Stephen Strogatz coming soon. And we have a special lecture on the notion of time with Craig Callender, my colleague here at UC San Diego, which was in person back in the spring, and Anthony Aguirre, our colleague up in UC Santa Cruz. I can't wait to share all these with you. So sit back as we go into the impossible with Dr. Brandon Hensley and yours truly, Dr. Brian Keating. Enjoy.
And just to highlight the importance of it, the search for cosmic microwave background B-mode polarization is incredibly interesting to cosmologists and astroparticle physicists around the world to hopefully unravel our cosmic origins, or perhaps reveal information about the primordial universe and the fluctuations that led to it. But equally important are perhaps the presence of tiny departures from Lorentz invariance that may signal departures from the fundamental symmetries that underpin both quantum mechanics and relativity as a whole. And these are symmetries that are perhaps held even more dearly than is the symmetry that underpins the theory of cosmic inflation. So in some sense, detecting a departure from Lorentz invariance or parity violation, these would be even more revolutionary, stupendous, and exciting for cosmologists such as ourselves and our colleagues around the world with telescopes like the Simons Observatory, Simons Array, ACT, BICEP Array, etc. So with that, I'm going to turn it over to Brendan Hensley, who's a longtime friend and a brilliant intellect. And also, I don't know if Brendan's aware of this, but Lyman Spitzer, of course, was the progenitor and the namesake of the Spitzer Space Telescope. He was a professor at Princeton University, but he's also the father of Lyman Spitzer is the father of Nicholas Spitzer, who's a professor at UC San Diego of neurobiology. So I find that very exciting, and he's a friend of mine as well. Anyway, with that, I turn it over to Dr. Brendan Hensley. Thank you, Brendan.
Well, thank you so much, Brian. I'm really pleased to be here today, and do wish I got to join you in San Diego, but hopefully sometime soon. And no, I didn't know that about Lyman Spitzer's son. That's really neat. Brilliant introduction to what I'm going to talk about today in terms of the importance of cosmic birefringence. And recently there was a claimed hint of this cosmic birefringence signal at kind of the 2.5 sigma level, looking at doing a reanalysis of the Planck data with a pretty clever technique for how to tease out this birefringence signal. However, as with the search for primordial B modes, one thing that we have to worry about is what the dust in our galaxy is doing and whether it can create signals that might interfere with our inference of these primordial signals. So I'm going to now leave the high redshift universe and spend most of my talk here in our galaxy. And I decided to prepare a few slides before diving into the paper because it requires a little bit of buildup of kind of what's going on in the interstellar medium to appreciate the tests that we're doing in this paper, where we think we have pretty compelling evidence that we now understand how that dust is creating these parity violating signals, and two, that it's related to the fact of how structures in the ISM are arranged into these filamentary structures, and which has implications for these studies of cosmic birefringence. So I'm going to go through the let me see, slides. Okay, they're working now. So the motivation for these slides is really just to try to give you a kind of schematic. It's really a geometric picture of what we think is going on with these ISM filaments, to kind of set up the analysis that we do in the paper, and then we can walk through that in some detail. And so indeed, so the main takeaway is that we provide observational evidence that this kind of filament model that explains the dust E to B asymmetry, the TE correlation, and the non-zero TB is in fact correct. And we can use this framework to make predictions for the EB correlation in the polarized dust emission. So I don't know what your usual protocols are, but I'm certainly happy to be interrupted at any time with questions. So please do that. Okay, so the first thing to appreciate is where dust polarization actually comes from to begin with. And you need two ingredients in order to get dust polarization. One is that your dust grains have to be aspherical. So I here have it illustrated as a football because I find that easiest to think about. Because an aspherical grain, so your wavelengths that are much larger, much longer than the sizes of your grain. So typical interstellar dust grain is about 0.1 microns. We're talking about millimeter wavelengths. So the photon wavelengths are very long. And so the grain actually both absorbs and emits photons preferentially with electric field oscillating along its long axis rather than its short axis. And so that gives an individual grain a sense of polarization in the radiation that it emits. But if you just had a collection of randomly oriented dust grains, even if they were all aspherical, you wouldn't get any net polarization because it all average out unless they were systematically aligned. And so what happens is that first, the dust grains tend to rotate about their short axes. And if you've ever tried to throw a football, you will know that it's much harder to get the football to rotate around its long axis, a nice spiral, than it is to tumble about its short axis. So things tend to prefer to rotate about its short axis. And then the short axis, which is the rotation axis of the grain, tends to align with a local magnetic field. And this is due to effects of paramagnetic dissipation. Basically, a rotating grain that is made out of some paramagnetic material, has some unpaired electrons in it. When it rotates, it'll get magnetized, develop a magnetic moment along the rotation axis, and then the magnetic field is going to exert a torque on that magnetic moment in every configuration except in the configuration where the angular momentum vector is aligned parallel to the magnetic field. So that rotational kinetic energy associated with J not parallel to B gets dissipated away as heat, such that over time, the rotation axis, which is the short axis, gets aligned with the local magnetic field, and then the sense of polarization is perpendicular to magnetic field lines, since the long axis is perpendicular to the field. And that's the orientation it likes to emit its photons. So that means that if we observe dust polarization and can measure the dust polarization angle, we can do a really good job at tracing the orientation of galactic magnetic fields. And that certainly has emerged as a very powerful probe, especially within the last decade with observations from Planck and then at shorter wavelengths with things like SOFIA. Okay, so that's the number one ingredient, is that dust grains are aligned with magnetic fields, and that's what gives us the dust polarization. The second observational fact that we need here is the fact that dust and gas are well coupled. So certainly in the diffuse atomic medium, where most of your hydrogen is in atomic rather than molecular form, about 40% of the sky, and basically anything that you're going to look at and try to analyze in a cosmological analysis, the mass ratio of dust to gas is relatively constant. So in this plot from an earlier paper of mine, just showing the correlation between the dust reddening, so how much optical photons dust absorbs, versus the hydrogen collimancy, just how much H1 gas you have along the line of sight. And you see that they have a very strong correlation, deviations at kind of the 10% level or less. And some of that might actually just be due to the EBV measurements rather than the intrinsic tightness of that correlation. So for much of the sky that we would be analyzing for cosmology, if we know the hydrogen column, we can make a pretty good guess at how much dust we have on that line of sight. The next datum that we need to get this picture is the fact that the gas is arranged in filaments that are coupled to the magnetic fields. So to understand this, if you consider a blob of gas, as on the screen here, sitting in a magnetic field, if you have any kind of MHD turbulence, any kind of shear, it's a lot easier to stretch that thing along field lines than it is to move anything perpendicular to field lines, such that over time you would end up with something that gets kind of elongated along magnetic field lines. And so the idea here is, if we can see these little filamentary gas structures in our H1 emission data, then that is another probe of galactic magnetic fields, since these little H1 filaments tend to be preferentially elongated along the field lines, organized into these linear structures. And so you might be wondering how that's possible, because I'm talking about neutral atomic gas. So how does neutral gas know about magnetic fields? And this is a phenomenon that's called flux freezing. Even in the atomic gas in the interstellar medium, the ionization fraction, it doesn't have to be very high. Talking, I think less than 10 to the minus 4 ionization fractions are sufficient for the ions and neutrals to be collisionally coupled to each other. So the ions are tied to the field, and then the ions are also collisionally coupled to the neutrals. So effectively, the magnetic field lines get frozen into the gas. The neutrals are coupled to the field as well. So even though we're talking about mostly neutral gas, it does still know about these magnetic field lines, and thus about dust polarization. And so this is work that is pioneered by Susan Clark, who's the lead on the paper that I'll be talking about today, of using the morphology of H1 maps to deduce these filament orientations. And this is using a technique from machine vision known as the Huff transform, and generalized to the rolling Huff transform, where basically you take raw data. So this is H1 emission at some particular H1 velocity. And we're going to take that data, and we're basically just going to look for lines in that data. So we're going to high pass filter it, and then see if there's any directions relative to some given pixel where, if you look along a line, then you see emission that is correlated along that line. And so basically you take this, you apply this transform, and you get an image out that looks like this, where now essentially this has picked out all of the linear features in this image. And so the idea would be is if we're able to apply this transformation to our H1 data, we are essentially picking out the filaments and therefore picking out the magnetic field lines. And so, this particular little filament, it seems like it's oriented in this direction. So we would guess in this region of the sky, the magnetic field is oriented like that, and that would also allow us to predict what the dust polarization angle is. So in 2015, Susan Clark and Colin Hill and collaborators showed that this actually works extremely, extremely well in reproducing the morphology of the polarization angles in the dust as seen by Planck, for instance. So at the top, you have in this, the Van Gogh style line integral convolution method of plotting these magnetic field lines. Magnetic field orientation just completely inferred from this H1 data, just from 21 centimeter emission from neutral hydrogen, and applying this algorithm and finding where all the linear structures are, and then saying that those trace the magnetic field. And if you compare that to the dust polarization angles from Planck, you see very good agreement. And these little white vectors that you're seeing on here are actually where we have measurements of stellar polarization. And it's the same dust that gives us the stellar polarization as gives us the far infrared polarized emission. And those polarization angles agree very well as well. So in 2019, Susan and I had a paper where we kind of took the next step in this is, not only can we predict these angles, but we can actually just predict the total level of emission as well, using the fact that the dust and gas are well coupled. So if you know how much gas you have, you know how much dust you have. And so we created these synthetic H1 based Q and U maps, where again, the angle information is just coming from this filament finding idea. And then the total polarized intensity is just coming from how much hydrogen gas you have. And so this is just our maps of Q and U purely from the H1 data. And then this is the Planck 353 gigahertz Q and U maps. And you see that the H1 data just by itself, and there's no parameter tuning or anything like that in there. The only thing is that the maps aren't even in the same units. So there's some overall one number scale factor applied to the whole map. But you see that the H1 data just by itself is able to reproduce so much of what we see in the polarized dust emission in the Planck data. Okay, another useful tidbit before we dive into the paper is about the E to B asymmetry. So one of the things that was kind of surprising that Planck found when analyzing the polarized dust emission is that if you do the standard E and B mode decomposition, you find that dust generates about twice as many E modes as B modes. And this was not something that had been predicted a priori. And so we took our H1 maps, so we have H1I, Q, and U maps, and we're able to compute the B to E ratio in those maps. And what we find is very good agreement with what is seen in Planck. So this is the single number that best fits the Planck data over this multiple range over the mask that we used, which is just half the sky. And this was our L by L measurement of the B to E ratio just in our pure H1 maps. And it's kind of remarkable that one is able to do this without any kind of dust modeling at all. We've really only said that the dust is following whatever the gas is doing, both in terms of the orientation and in terms of just the total intensity. So this is pretty strong confirmation of a kind of filament interpretation of the dust emission. So if we go back to this paper from 2001 by Matias Zaldarriaga, has this very nice explanation of the decomposition into E and B modes of emission in an elongated density structure. So now you can imagine each of these little tubes here is one of our H1 filaments, and then the little vectors in there are just saying how the magnetic field is oriented relative to the filament itself, or really how the sense of polarization, which is set by the magnetic field for the dust emission. And so what he showed was that in these first two cases, where you have the magnetic fields or the sense of polarization either perpendicular to or parallel with the filaments, this produces E-mode polarization. Whereas if you have your sense of polarization is tilted at a 45-degree angle relative to your density structure, then this gives you preferentially B-mode polarization. And so this really aligns with our expectation from these interstellar filaments, where we have these elongated density structures that we think the magnetic field is running parallel to. And so our polarization is perpendicular to these filaments, which gives us mostly E-mode polarization. And so maybe it's not surprising after all that the dust produces more E-modes than B-modes. And also we get a very strong correlation between the temperature and the E-mode polarization in the polarized dust emission. So this is all very naturally explained in this filament picture, and it's also very gratifying to be able to reproduce this just with the pure H1 data without doing any kind of dust modeling, because really that does rely on kind of this filament picture. So now the question is, what about TB? So we can understand that we get this TE correlation from the fact that our magnetic fields are threading these filaments, but TB is a little bit more difficult to understand in this context. There's from Planck, there was some hints that the dust emission had non-zero TB, and a paper from Weiland et al. In 2019 that did a number of tests on this to kind of assess its robustness. And it really seems like, at least at large angular scales, the polarized dust emission indeed has a preferentially positive non-zero TB. It was shown by Kevin Huffenberger and collaborators that this could be explained if, instead of the magnetic field perfectly threading this filament, you had a slight offset in the angle of the orientation of the filament versus the magnetic field. So just like in the image I showed you previously, if you have your magnetic field at an oblique angle to your filament, then that can generate some B-mode polarization. But in order to have a robustly positive or negative TB across a large area of the sky, then that means that all of your filaments would have to be rotated relative to your magnetic field, preferentially in one direction or the other. So they're all tilted, 5 degrees counterclockwise on average, or 5 degrees clockwise on average, to be able to see the level of TB that we observe. And so that certainly was not expected. One would say if you have, a ton of these little interstellar filaments, then they're all going to, even if, it's not uncommon to have an offset between the filament axis and the magnetic field, by the time you average over all the elements, all the filaments, why would you have any persistent, sense of twist or angle offset left? So that was what was a bit unclear. It is also emphasized by this Huffenberger et al. Paper that if this is the explanation for dust TB, then it necessarily implies that the dust EB is non-zero. And that's what the potential problem is for birefringence analyses that typically assume that the intrinsic EB correlation from the galaxy is zero. How can we study this parity violation in the dust emission and assess whether or not it's really coming from this kind of misaligned filaments picture? And so in this paper, what we really have are two independent measures of each of these angles. So from our H1 maps that I've introduced, we have already measured the orientation of the filaments on the sky. So we know this angle. And then from the Planck 353 gigahertz polarization data, we know what the dust polarization angle is, and therefore we think we know what the magnetic field orientation is. So we can actually measure for every pixel on the sky what the angle difference is between our filament orientation and our dust polarization angle. And if this picture is right, then we should see that this delta theta, this signed difference between these two angles, and the signed is important because remember it has to be a systematic, clockwise twist or a systematic counterclockwise twist. So we can map this this delta theta, and it should be predictive of what's going on in the dust TB. So that's kind of the setup. before I dive into the paper itself, is there any questions or anything I should go back over?
You just talk about how TB would originate from that mechanism?
How TB is generated?
Yeah.
Yeah, so I won't be able to derive the math on the spot, but the Zaldariaga paper does a really nice job of it, showing that if you imagine you had a single, just one filament, and the sense of polarization, so one filament in temperature, or total intensity, and the sense of polarization for emission coming from that filament is oriented obliquely to that filament, so at a 45-degree angle is where you get maximum TB correlation. Then you preferentially produce a B-mode polarization, and thus a TB signature. The tricky thing about TB is, the sign is what matters here. For TE, we naturally expect every single filament on the sky to have the magnetic field threading the filament. It's not going to be, half of them are parallel to the filament and half of them are perpendicular. It's going to be, they're all parallel. Whereas, in this B mode picture, you could say, okay, well, yes, sometimes maybe you'll have a 45-degree or 5-degree or whatever inclination between your magnetic field and your filament, but you would expect that to average to 0 after you averaged over a bunch of filaments, because there's no reason why that 5-degree offset ought to have the same sign for every single filament, either clockwise or counterclockwise. So that's why we wouldn't have expected any TB correlation.
Thanks.
Mm-hmm. Okay, so let me see if I can switch things elegantly. All right, can you see the paper?
Yep.
Excellent. Okay, right. So the origin of parity violation and polarized dust emission and implication for cosmic birefringence. So we claim that we think, we understand the origin of this parity violation. We think that, we demonstrate that this is coming from these misaligned filaments. So the first thing that we show in this paper is the fact that the TB correlation as measured is robust. So here is a measurement of the 353 gigahertz cross 353 gigahertz TB correlation in the Planck data. So this is now using the in-pipe maps rather than the PR3 maps. And you see its TB is pretty robustly positive, from about L of 100 to 500 or so. So that seems pretty solid. And this black line is a fit not to these data, but to, it was from the Planck paper, a fit to the exact data that they used. And you see, the magnitude of TB is about what we see here using the in-pipe maps. But we can assess the robustness of this to various systematics by swapping out some of these maps. So the 353 gigahertz polarization map is pretty much the best dust polarization map that we have. That's over a very large sky area. So not really much to be done there, but we have lots of maps of dust intensity that we could use as the T in this TB correlation. So we tried it with the Planck 857 gigahertz data and also using the H1 maps. And in every case, we see what appears to be a preference for a positive TB correlation. And so, we think that this is real and this is astrophysical. And now let's see if we can understand what's going on here. All right, so the two figures here. On the right here, in figure 3, is a plot of this delta theta that I introduced in the slides. So this is taking the signed angle difference between our little H1 filaments that we've identified, and then the 353 gigahertz polarization angle. And this is what we claim will be predictive of what the dust TB is doing. And now you'll be able to see rather immediately that, there's not a lot of large scale structure in this map. This delta theta is kind of all over the place. So, this will have some implications for thinking about how to mask this. Okay, and then on the left here is kind of a visual explainer of what we think all of these different correlations ought to be doing as we consider a rotation angle between the filament and the magnetic field orientation. So if the magnetic field and the filament are perfectly lined up with each other, which I would say is kind of the standard case, then we'll see a robustly positive TE correlation and no TB or EB correlations. That those will just all average out. It was gratifying to see that when we looked for TB in our H1 maps alone, so H1 intensity cross H1 B modes constructed from our synthetic Q and U maps, we didn't see any TB correlation. And that makes sense because those maps were constructed under the assumption that the filament axes are the polarization angle. So that gives us 0 TB correlation for H1 maps. And so these actually are this angle. Let me explain that. So the 0 is kind of just the out of the box H1 maps. And then we can imagine applying a global rotation over the whole map to our polarization angles. So I'm going to take the polarization angle in every pixel, and I'm going to rotate it by some angle, and some sine angle, either clockwise or counterclockwise. And what we find as we rotate this angle, we start generating the TB and EB correlations. So, start to rotate this angle in one direction, then EB and TB become positive. So now, every single, filament is now offset by its magnetic field by some, angle counterclockwise here. And the more we do that, the greater the TB signal we generate is, and also the TE signal goes down, because we're kind of moving into that regime from the Zaldariaga 2001 paper, where now you have the filament axis and then the magnetic fields at a 45-degree angle, to eventually where the TB is maximum and then the TE is 0, and then the EB is also 0 in that case. And then it goes back as we rotate it back to pi over 2, and the same thing negative. So this is a very nice, purely from the data demonstration that as we apply a global rotation to all the polarization angles over this map, which is effectively, because we're not changing the intensity maps, so all the intensity structures are, stay put where they are. We're just rotating the polarization angles relative to these intensity structures, and we're able to generate TB and EB correlations just from doing that. Okay, so now can we construct an empirical test that convinces us that this angle difference between the H1 filaments and then the Planck measured magnetic fields really knows something about TB. And so what we do here is, maybe I'll go back to this map quickly. So we take this map of our delta theta, which is an observed quantity, and we would say that 1 sine of delta theta should be associated with 1 sine of TB. So as we rotate, clockwise, we'll go here, and as we rotate counterclockwise, we'll go here, and then the other sign will be associated with the other sign of TB. So the idea that we had was, okay, why don't we take half the map that has the positive delta thetas and keep those exactly the way they are, but then for the part of the map that has the negative delta thetas, we'll just mix them up. We'll just apply a random rotation to every pixel. And so the idea is that we'll destroy any TB correlations associated with these negative delta thetas and keep only the ones associated with the positive delta thetas. And so that should really boost our TB signal. And if we do the opposite, destroy all of the positive ones and keep only the negative ones, then we should, again, boost our TB signal, but it should have the opposite sign, because we've gone from, this branch of TB down to this branch of TB. And so that would be our observational test. Maybe the most elegant thing that one could have done would just be to mask all of the negative ones and take the power spectrum of all the positive ones. But one look at that mask and you'll see exactly why that's not practical. There's just so much small scale structure in there. You'd never be able to construct a sensibly behaving mask. So that's why we've done this angle randomization idea. And so, so we do that. So we construct some null tests where we, rather than select on the positive or negative, we choose, just random pixels, and we don't really, we see something that's mostly consistent with our original map, which is good. And then we do our two tests, one where we keep just our positive angles, and one where we keep just our negative angles and scramble the rest. And what we see is that in the one case, we see this robustly positive TB correlation, much larger than what is seen in the original data. And then in the other case, not only do we destroy that correlation, but we actually make it negative by keeping only these negative delta thetas. We see this robustly negative TB correlation when we only keep our negative angles. And so that tells us immediately that it really is this delta theta that knows what the sign of TB ought to be. Because just by choosing which pixels that we do our analysis on, by virtue of this sign of delta theta, we're able to generate either robustly positive or robustly negative TB signals. And it would be hard to understand how this could be the case unless this underlying filamentary picture is the correct one for explaining these correlations. So we can do the same thing with EB. This plot demonstrates very nicely that as we generate TB correlations, we also generate EB correlations. And so when we measure these EB signals on our map where we've destroyed the correlations in half the pixels, we find that indeed we can generate very large, both positive and negative EB signals. The null is consistent with 0, the original maps are consistent with 0, but by selectively applying rotations to these positive or negative delta theta pixels, we can get these either positive or negative EB signals that have the sign exactly as we would expect. So this is good in the sense that this gives us a lot of confidence that this filament picture is the correct one, but that also means that given the fact that we do observe a positive TB correlation in the sky, that the EB correlation in the sky is going to be positive and non-zero as well. Any questions on that before I move to the kind of image D simulations portion of this?
I was wondering if you have a sense of why there's like a peak around L of 300 or so, or what the angular dependence is.
Yeah, why there's this little feature. Yeah, I'm not 100% sure what is going on there. I don't know if it's just a fluke fluctuation in the original map. Would probably be my guess. I mean,
okay, sure.
Yeah, I don't think there's any. Or are you saying why does it go back down to 0?
Yeah, or like why is there a peak?
Yeah, so I mean it certainly is. And we'll talk about the scale dependence a little bit in a bit, but we're really talking about physical filamentary structures in the ISM that are going to have some characteristic size and some characteristic aspect ratio. It's not ridiculous to think that there's going to be some scale dependence to this correlation. Some level will also matter, how much you're averaging down by looking at the very large scales. two or more filament terms kicking in versus looking more at single filaments. And then I think some of this will also just be noise in the polarization data as well. So I would say that from what we see, I wouldn't read too much into the detailed scale dependence. I think we'd be hard pressed to say that it's anything other than flat, but we certainly don't expect in detail for the scale dependence to be flat in L. And I think that'll be one of the interesting things to really follow up on and see if we can measure, because it absolutely measures for these birefringence measurements, whether you're parameterizing this as a scale dependent thing or not.
Oh yeah, definitely. That's what I'm thinking in terms of if you're going to try to remove it. So, okay, thanks. And then I just had another question on that map above where you showed the angles.
Yeah.
I was actually a little surprised to see so much red and blue. I guess I thought maybe this is an incorrect interpretation, but it looked like there's a lot of misalignment relative to what I would expect. In this picture of the gas aligning along the magnetic field line. So do you have a sense of why there's so much misalignment as opposed to like the naive picture of just they're all aligned?
Right. So this actually is a good segue into the next part of this, where we actually look at this in MHD simulations. And I would say that as it happens, the amount of misalignment that we're seeing here is not all that unusual relative to what is seen in actual ISM simulations. So the ISM is turbulent and messy. There's a lot going on. So it's perhaps not. I wouldn't have been able to predict a priori, what the dispersion in angles should be or anything like that. But it's perhaps not surprising that strong misalignments are not uncommon. And I should also say that when you get into really dense gas, and this will become important in a second, you can actually get into the regime where the alignment is actually the opposite. You're in more of one of these situations. Because if you have a lot of gas that piles up along field lines, so you start kind of making a pancake, and that gives you a filament that's perpendicular to your field lines. And so that's something that can happen in very high density regions. And that could give you negative TE correlations in these high density regions, which there's kind of some hints of in Planck data. So in reality, there's a whole spectrum of very clean, nicely threaded filaments with a magnetic field, and a lot of turbulent motions and whatnot, making things a lot more complicated.
Sure, I see. Okay, thanks.
Yeah. Yeah, and then there's also, I guess you can see by eye a little bit of 3D, a little bit of coherent, where it's particularly white, particularly close to zero, in kind of these large areas. And that's actually related a bit to the 3D effects, whereas on a single line of sight, you might be looking at multiple filaments. And so you're only measuring one dust polarization angle that's kind of the weighted average of everything you're seeing along the line of sight. And so that's another way that that things can be different. So these are actually these preferentially white regions are highlighting regions of particularly low polarization fraction. Okay, so let me talk about the MHD sims a little bit since we got into that. So that's this figure here. So we're looking at, so this is real data using the in-pipe data, using the 857 gigahertz for temperature, because it's the highest signal to noise being at the highest frequency, and then 353 gigahertz E and B. And then these are MHD simulations put together by Chang-Gu Kim. So using the Tigris code. So this is like a huge slice of a galactic disk, kind of 1 kpc by 1 kpc in the disk, and then 7 kpc above and below the disk. So these kind of huge rectangular slices of galaxy, and he has a lot of these. It's full MHD with star formation and self-gravity. It's really done to study the interstellar physics, but what he has found is that he does a pretty good job at simulating what we see in CMB data by putting a little observer inside his simulation cubes and saying, oh, what does the sky look like to this observer? And the virtue of this, or one of the many virtues really, is the fact that we can get a ton of different skies just by putting this little observer in different places in the galactic plane, and then also just by the fact that these are time-dependent simulations. And so he in previous work has shown that things, even like the E to B asymmetry, can have a time dependence to them. It's you don't necessarily generically get this 2 to 1, that it depends a little bit on if a supernova has gone off near you recently and kind of moved everything around a bit or whatnot. So he gets a wide range of skies that don't have necessarily the statistics of the sky that we know and love. Okay, so this is showing the cross correlations between these various quantities in the impact data, and then also the simulation maps. And this lets us do things like test in detail whether we see the expected correlations between, say, TB and EB, for instance, in the simulations. So let me see if I can. Yeah, so I think this is possibly more illustrative than just throwing up all the correlations on there. So if we are in a scenario like we are in the real sky, where we measure this positive TE correlation, then the correlation between TB and EB is positive. And so if we just take his, each one of these dots is a different simulation, or at least a different observer in a simulation at a particular snapshot, and measure what the TB correlation is and what the EB correlation is in the dust emission, then we see very strongly this positive correlation between EB and TB as predicted. Right, and then, so this is between EB and TB, and then this is between EB and TE. And now, by virtue of these simulations, we also get some skies where the TE is preferentially negative. We just happen to be more, have more in the regime of filaments perpendicular to field lines, for instance. And in this case, if we go back to this figure here, so if TE is positive, like we see in the sky, robustly positive, then TB and EB are positively correlated. As long as we're close to 0 on this plot, we should see a positive correlation. But if we go to somewhere where TE is negative, then you'll see that the TB and EB are negatively correlated. And that's exactly what we're seeing in these simulations, where now we're going to skies that have this negative TE, and we're seeing this negative correlation now between TB and EB. And so this very much goes with what we would have expected just from the interstellar filament picture. Maybe the other thing to note is that across these simulations, the E to B ratio is reasonably stable, I would say. Not a lot of variation in it, but EB and TB and TE really all can have substantial variations. And so kind of the way we've wrapped our minds around this is really, there isn't some, intrinsic parity violating physics in the dust emission itself, or in the MHD or whatever. It really just is just the realization of the sky that we happen to get sitting in our particular location in the galaxy, that there's enough stochastic variation in this that it doesn't all just average down to 0 and we get a little bit left over. And whether that little bit left over happened to be a positive TB or a negative TB was more or less up to chance, and we got what we happened to get. But the good thing about that is, assuming this is the right underlying picture, is that by measuring this TB, we can predict what the EB is. And so that's what the last portion of the paper is focusing on, is thinking about this in terms of the birefringence analyses, and particularly this paper by Minami and Komatsu in 2020, who made a tentative claim for a cosmic birefringence. So in this image here, essentially what we've done is applied a mask to the data. So this is our the Planck 70% galaxy mask that we use in all of our default analyses. And we measure a TB, and we can convert that into an angle, if I can find the right. So we can convert that into an angle, which is effectively saying, how much do we have to systematically misalign the magnetic field from these filaments in order to produce a TB signal as large as what we measure? So, Huffenberger et al. Did a similar kind of analytic calculation, and they found that 5 degrees seemed to be enough. That if you had kind of a 5-degree preference for a clockwise rotation versus the counterclockwise rotation, then that would give you the that would give you the TB of the size that we measure. And so this is taking the TB that we measure over this specific mask and saying how big of an angle is it? And indeed, we see something that's about 5 degrees. And it's important to to emphasize that this is much, much, much larger than the quoted systematic uncertainty on the angle calibration, which is down there at point a few degrees, and also much larger than the cosmic birefringence angle that was quoted, is also something like point a few degrees. So we're really seeing something more like 5 degrees. So if the Minami and Komatsu analysis had been on this mask, and we had seen a robustly positive TB that could be contributing a robustly positive EB to the dust emission, then we would have said, oh, so actually the Minami and Komatsu result is a lower limit on cosmic birefringence, and their detection, or their hint, is actually a little bit more statistically significant than they quoted, because this would only serve to make that smaller rather than larger. And then all would be great. However, they didn't do their analysis on this mask. They did their analysis on this mask. So they're much more aggressive in terms of how deep into the galactic plane that they are reaching. So using kind of 90% of the sky rather than 70% of the sky. And when we compute TB over this mask, we don't get this nice robustly positive TB. We see TB that maybe is positive at large scales and maybe dips negative and then maybe is 0. It seems a much more complicated and certainly has some non-trivial scale dependence to it. And so we can't really say too much quantitative about the Minami and Komatsu analysis because we don't see a very cleanly behaved TB signal. So this really underscores one of the points that we try to make in this paper, is that given the origins of this TB signal and the consequent EB signal, is that your answer is going to be really mask dependent, depending on just what part of the galaxy you happen to be looking at. And so, one of the things that we recommend is it'd be nice to redo the analysis on a mask like this, where the TB is a lot better behaved and doesn't have this really strong scale dependence.
Since the data are public, can you just do that analysis?
One certainly could. I don't know that I could sit down and implement it out of the box, but I'm sure that there's somebody working on it right now. And would definitely be a very interesting thing to do. I don't know how much presumably they went to this very aggressive sky mask because they needed all of the signal to noise. So I don't know if one will get into difficulties on that account.
That's right.
Right. So the things to emphasize here, yes, is this is very mask dependent, but we can measure TB over, at least if we have a reasonable sky area. And we can make sure that we're doing these analyses on mask where this is well behaved. But I think, the real answer is to implement this, a full likelihood approach, taking into account any possible scale dependence of this correlation, because we certainly don't. Looking at this, you would say, okay, that doesn't look like there's any very dramatic scale dependence over, kind of the 100 to 500 L range. But again, this is coming from real interstellar filaments that have real physical sizes, and will have some size and distance distribution. So this will almost certainly have some scale dependence once we dig in far enough. So it really should be accounted for in any analysis as well.
Oh, yeah. So I just have a quick question on, on how exactly to account for that. So is it possible to basically just, give it the sky mask? I mean, so really they use CLEB, right, to estimate the rotation angle. Could you basically give them, here's the CLEB we expect from dust, and could they run that through their pipeline and generate the angle based solely on dust they would expect?
I mean, I think that's effectively, that's kind of what we do for the mask here. Although, of course, it doesn't turn out into a nice single angle over that full L range. But I mean, this is us, translating these measurements into a rotation angle.
Maybe I was a little bit confused. So is there a distinction between the rotation angle of the misalignment between the dust, the gas filaments in the magnetic field versus like a global rotation that would generate, EB?
Right. So when we're talking about this angle here, we really do mean it as kind of a global rotation. So naturally, we would expect that each filament to be doing its own thing, and that this angle is only the statistical thing that comes out at the end, that you end up on average biased by this many degrees in one direction or the other. And so that can be effectively parameterized as a single global rotation. But then that becomes degenerate with any other kind of global rotation, whether that be, just your polarization angle is miscalibrated by a few degrees or whatever, one direction or the other, would also look like this. And so one of the points that we make is that this number that comes out is actually much larger than that particular uncertainty.
Yeah. Okay. All right, thanks.
Mm-hmm. Yeah, and I guess I should also say that, given the fact that we do measure a TB and a TE, we can kind of use this picture here to figure out, where on these curves that we fall, and to estimate what EB is. And the Planck data are not sensitive enough to be able to measure the level of EB that we predict, but it's also not ridiculously low. So it's certainly something that could be pursued with more sensitive data. I think I think it will be a matter of time before we make the first dust EB detection.
So it's exactly the opposite as in the cosmic case, potentially, where EB dominates over TB if parity violation exists. Well, thanks, Brendan. Is that the end of your presentation?
Yep, that's. I think I got through everything. Unless there's any other questions or anything else to discuss.
In terms of self-calibration, using the galaxy essentially to null out cosmic birefringence, there's one issue is that we don't have a guarantee that there's no not cosmic, but astrophysical polarization rotation on galactic scales. Mm-hmm. We haven't really tested it beyond our solar system, really. So, is it a fraught proposition to do as Mianmi and Komatsu are suggesting, essentially to use the galactic
treat the galactic contribution as a calibration source. If indeed, effects like this could be intrinsic. I know they're treating it as a lower limit and it would only get stronger, but you're showing its mass dependence. No one's been able to use the galaxy as just an E-mode polarization calibration source, to my knowledge, let alone a parity violation calibration source.
Yeah, that's a good and subtle question. Yeah, I'm not sure how far we will able to be to push this, but I mean, I think the Minami and Komatsu approach is a good one. I think it just needs to a little bit more sophistication to take into account these complications.
Great. Okay, so for those watching on my YouTube channel, I'm going to put a link here to a talk that I gave with Sean Carroll following the Komatsu paper results about their interpretation, if it's true. And you'll want to see that talk for background from the person who came up along with colleagues back in 1990 with the astrophysical implications of cosmic polarization rotation. And so click this link over here. I don't know if you can see me, but I'm pointing somewhere over here. And with that, I want to thank Brandon very much. Brandon, have a great rest of your day. Thanks for this wonderful talk.
It was a pleasure. Thank you all.
Bye, guys.
Thanks, Brandon.
Thank you.